Hello students, let us now study our today's topic, which is springs. So we are all familiar with the spring. So suppose I draw a spring here. Now, if I apply a force on the spring from either side, from either left side or right side, then the spring may get elongated. If the right side is fixed, then on applying a force capital F on the left side, we can see that there will be a extension in the spring. So the spring will get elongated. So this is the new diagram of the spring with elongation. Suppose the extension in the spring is X, then we can say the force in the spring due to this extension is directly proportional to the extension. Isn't it logical? More the extension, more will be the force in the spring. So we can say spring force is directly proportional to the extension X. So our equation for spring force becomes force in the spring is directly proportional to the extension X, or force in the spring is directly proportional to the compression X. So we can say force in spring is equal to some constant K into X. So our equation for spring force becomes F is equal to Kx, where K is a constant called as spring constant, and X is the extension in the spring or compression in the spring. So if we compress the spring, this is the natural length of the spring, let us say L0, and I compress the spring by some value, let us say X, then in that case the spring force will still be Kx. Now, what is the direction of extension? If I talk about the extension in this case, so in this case, extension direction is towards the left. Then the spring force will act towards the right. So let me make you understand this. This is a spring in natural length. Suppose we have a mass M here on which I am applying a force. Now, after some time, what will happen? There will be elongation in the spring. So the spring will get elongated due to this force. So the extension in the spring is in right direction, but the force of spring is in the left direction. The force of spring is in the left direction. Extension is in the right direction. So we can say force is directly proportional to X. So force is Kx, but exactly speaking, force is minus Kx. Why do we have a negative sign here? Because negative sign shows that force in the spring is opposite to extension in this case. So force F in the spring is opposite to extension X. So this is the meaning of negative sign in this expression. Force and extension, they are opposite sign. Extension is towards the right, force in spring is towards the left. Whereas the applied force is in the right direction. This is applied force. We are talking about force in spring. So force in spring is towards left because the spring will pull the mass in this case. Now, second case, let us consider compression in the spring. Suppose this is a spring in natural length. Now, Suppose I apply a force on the spring mass in left direction, which will be eventually transferred to the spring as well. So in that case, what we can say, the spring will undergo compression. So this is the new diagram of the spring. The spring has been compressed by a value x. So in this case, the direction of force in spring will be towards the right, because when we compress the spring force acts in right direction. If we compress the spring, then the spring force acts in right direction. So this is what is the diagram. So we can say force in spring is directly proportional to x, which is the compression. So we can say spring force is equal to k into x, where k is a constant. As I told you, it is spring constant. Again, if I talk about the equation of the spring force, it will be F is minus kx. What does negative sign here show? Negative sign shows that the compression in this case is towards the left. The compression is towards left, whereas the spring force is towards right. So that is compression and spring force, they are opposite in direction. So this is how we have the equation of spring force. So to sum it up, what we can say, spring force F is minus kx. Note, negative sign shows spring force and extension or compression are in opposite directions. So this is the formula for spring force. F is minus kx. X is extension or compression. K is constant, which is called as spring constant. And X is the extension or compression in the spring. If I talk about the magnitude of spring force, it will be kx. So magnitude of spring force will be kx. So if someone asks what is the value of spring force, we can directly use this equation, which is magnitude of spring force is kx. Now, let us consider various cases. So first case, let us consider if we have two springs in series. So let us say we have two springs in series. So let us say we have a situation in which we have one spring having spring constant K1 and another spring having spring constant K2. They are joined in series and they are connected to a mass. Suppose this is the wall and this is the horizontal surface, and here we have two springs having spring constants K1 and K2. So let me write here K2, let me write here K2. Now I want to find the equivalent spring constant. So let us find equivalent spring constant. What does it mean? Instead of these two springs, I will have a new spring having spring constant K such that due to external force, it has same extension or compression. So if I apply an external force on this mass, the two springs will, let us say, have some extension X. If I apply the same force F on the mass, then the same extension X occurs in the equivalent spring. So let us try to find the equivalent spring constant for springs in series. So we have two springs in series connection, like resistors in series. So in this case, if I talk about the extension in first spring, let us say by a black color x1, and extension in second spring, it is x2. So x1 and x2 are the extensions in two springs. X1 is the extension in first spring, x2 is the extension in second spring, and x is the extension in equivalent spring. This is the equivalent spring. So what I can say, x equals x1 plus x2. Now, using F is equal to Kx, the magnitude of spring force F is equal to Kx, we get the equation in this case. So let us say we have in this case our value F1 is equal to K into X1, K1 X1, F2 is equal to K2 into X2. So in that case, X is X1 plus X2. So F is Kx. These are the three equations. F1 is K1 X1. This is the equation for first spring. F2 is K2 X2. This is the expression for second spring. F is Kx. This is the expression for equivalent spring. So now let us see. In this case, what we can say is magnitude of forces F1, F2, and F. They will be equal. So let us say F1, F2, and F, they are equal. Why? Because the two springs are in series. So both the springs will have same force F. So same force F in both the springs. So similarly, same force F in the equivalent spring. So from that, I can rewrite my equation of spring force for each spring as F is K1x1, F is K2x2, and F is equal to Kx. So from this, what I will get is value of x1, x2, and x. So x1 is F by K1, x2 is F by K2, and x is F by K from these three equations. Let me show you once again how did I write these equations. So from this first equation, we get x1 is F by K1. From the second equation, I will get x2 is F by K2. And from the third equation, I will get x is F by K. So these are the three equations which I want. X1 is F by K1, X2 is F by K2, X is F by K. So now let us substitute these values in our expression here. So F by K is F by K1 plus F by K2. So let us cancel these F's on both sides. So I'll get 1 upon K is 1 upon K1 plus 1 upon K2. So our final expression comes out to be 1 upon K is equal to 1 upon K1 plus 1 upon K2. Let me put a box in this equation because this is very, very important. This is what we try to find. So 1 upon K is 1 upon K1 plus 1 upon K2. So this is the expression for springs in series. So to summarize, if we have two springs which are in series having spring constants K1, K2, then we can replace them by an equivalent spring having spring constant K such that 1 upon K equivalent, which is 1 upon K, is equal to 1 upon K1 plus 1 upon K2. So I can replace these two springs by a spring of equivalent K, which is K1, K2 upon K1 plus K2. Why? 1 upon K is 1 upon K1 plus 1 upon K2. So cross multiplying 1 upon K is K1 plus K2 upon K1, K2. So K equivalent comes out to be K1, K2 upon K1 plus K2. So from this, I can get the value of K for springs in series as 1 upon K is equal to 1 upon K1 plus 1 upon K2, or K equivalent is K1 K2 upon K1 plus K2. So if we have two springs which are connected in series having spring constants K1 K2, then the equivalent spring will have spring constant K, which is K1 K2 upon K1 plus K2. In general, for n springs, so spring 1, spring 2, spring 3, and spring n here. So we have 1 upon K is 1 upon K1 plus 1 upon K2 plus 1 upon K3 and so on. So this is the expression for equivalent spring constant for springs in series. Now let us consider another case, springs in parallel. So let us consider we have two springs. So suppose we have in this case two springs which are connected in parallel. So this is a spring having spring constant K1. This is spring having spring constant K2. And these two springs are connected to some mass, let us say M. K1 spring constant, K2 spring constant, and we have a mass which is connected like this. So in this case, if I apply a force F, then what will be the extension? Both the springs are connected to same mass. So both will have same extension. The mass M would have gone in forward direction due to this force F, and the spring will be elongated as shown in the new diagram by some value, let us say X. So we can say in both the springs we have same elongation X. So we can say in this case F, the spring force in equivalent spring. Suppose I consider the equivalent spring instead of these two springs. I have one spring which is having equivalent value. So then in that case for a force F, we will have extension X in the spring. So what will be the equation? F is equal to F1 plus F2, isn't it? For springs in parallel, we will have F is F1 plus F2. So F1 force, F2 force, and this is F force here. Okay. So F is F1 plus F2. So we can say K into X is K1 into X plus K2 into X. Why? Because for the equivalent spring, we will have equation F is Kx. For this spring, we will have equation F is equal to K1x, F1 is equal to K1x. For this spring, we will have F2 is equal to K2x. So instead of F, I have Kx. Instead of F1, I have K1x. Instead of F2, I have K2x. So x cancels on both sides and we get K is equal to K1 plus K2. So our expression for springs in series, so our expression for springs in parallel, it comes out to be K is equal to K1 plus K2. So to summarize, if we have two springs in series, then its equivalent spring constant K is given by the expression 1 upon K is 1 upon K1 plus 1 upon K2. And if we have two springs which are connected in parallel, K1 and K2, they are connected in parallel. So then in that case, we will have equivalent spring K. It will be K is equal to K1 plus K2. This result, if you notice, it is opposite to the ones for resistances which we studied. So if you remember, for resistances in series, we have R equivalent is R1 plus R2. This is for resistances in series. For resistances in parallel, we have 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. So in this case, for series spring, we have 1 upon K series is 1 upon K1 plus 1 upon K2. For springs in parallel, we have K is equal to K1 plus K2. So these are the equations which we need to remember for springs in series and springs in parallel. Now, let us do some illustrative examples based on this concept. So the first illustrative example which we'll take from our class notes is illustration 35. So in illustration 35, we have a smooth semicircular wire track having radius r. And here we have a spring as connected. Let me draw the spring once more. It is connected to a point P as shown here. This is the point P. Now, this angle which is made here with the vertical is 60 degree as per the question. And this is the center of semicircle C. Now, in this case, it is given to us a smooth semicircle track of radius r, one end of massless spring of natural length. So the natural length of the spring L0, it is given to us, it is 3r by 4. Natural length of spring is 3r by 4. So when it is at lowest point O, a small ring of mass small m which can slide on the track. So we have a small ring. Let me show that ring in red color. So this is the ring here in red color. It is tied to the spring. So this ring can move along the semicircular track. Now, it is given to us a small ring of mass small m is attached to other end of the spring. So this end of the spring is fixed. And this is movable end. The ring is held stationary at point P, so that spring makes angle 60 degree with the vertical. The spring constant, it is given to us as mg upon r. So spring constant K is mg upon r. Now in this case, we have to find the tangential acceleration of the ring. And we also have to find the normal reaction between ring and the track. So let us see how to solve this question. So first of all, let us think about the free body diagram. So in this case, what are the forces acting? Let us think. So one obvious force will be mg in downward direction for the ring. So let me mark this mg force in downward direction. Now, other than that, we have normal reaction. Let me show normal reaction like this. It is perpendicular to the surface. So let me draw it slightly better. It will be towards the center because normal to a circle meets at the center. So this is normal reaction N. Then we have spring constant, which is Kx. So spring constant is Kx. So these are the only three forces acting on the ring. So let me show the ring once again. Normal reaction towards the center, mg in vertically downward direction, and spring constant Kx, spring force Kx in between. So now let us think about the Newton's law equation. So what will be the change in length? So change in length of the spring, delta x. Change in length of the spring, delta x. So let us first calculate this value. So this is the free body diagram of the ring. Mg force in downward direction, normal reaction towards the center, and Kx towards the spring. Now, extension in spring, delta x, we will calculate it. The natural length of the spring is given as L0 is equal to 3r by 4. Now, by geometry, let us find the length of the spring in this position OP. So, let us calculate the value of OP. So this is OP. And if I construct this triangle, it will be a triangle like this, equilateral. because the C is center and this angle is given to us as 60, and this is radius R and R. So of course, if one angle of a isosceles triangle is 60, it is an equilateral triangle. So all angles are 60 and all sides are equal to R. So delta X will be R minus original length of the spring. So delta X is R, which is the length of the spring OP, minus natural length 3R by 4. So the extension in the spring will be 1 by 4R. So delta X comes out to be R by 4. So this is our first equation. Delta X is R by 4. Now, once we get this delta X is R by 4, let us consider in this case the Newton's law equation. Let me rub the unnecessary part. So if I get Newton's law equation here, so in this case, I will have to take the components. So in this case, we have change in length of the spring, which is R by 4. So spring force, let us first consider normal reaction N. Now if I take this value here, component of this mg, it will be mg cos 60. So I'll get the equation here as mg, this is kx. So if I consider the component of kx, it will be kx cos 60 as well. So component of kx is kx cos 60, because this angle is 60 degree here. So if I consider Newton's law equation, we will have n plus kx cos 60, that equals, in this case, mg cos 60. So this equation will get here. So n and kx cos 60 are towards the center, and mg cos 60 is in opposite direction. So n plus kx cos 60 is mg cos 60. Now, other than this, if I consider the length of the spring, so in this case, change in length, we got R by 4. Now, if I consider the equation of Newton's law for the spring, we will have mg upon 4 into cos 30 plus mg cos 30. This is equal to mass into acceleration. So in this case, the Newton's law equation will get. So how did I get this equation? So for that, let us think about the value. So in this case, let us think about the values. In this case, k value, it is given to us as mg by r, and x value, extension, we will get from this equation. It is r by 4 into cos 60, r cancels. So that is equal to mg cos 60. So we'll get our equation as n plus mg by 4 cos 60 is equal to mg cos 60. So our equation will come out to be, in this case, our equation will get n is equal to mg cos 60 minus mg cos 60 upon 4. So mg cos 60 into 3 by 4. Cos 60 is half. So it will be 3 by 8 into mg. So the value of normal reaction comes out to be 3 by 8 into mg. Now, in this case, what I am interested in is normal reaction in which value we found. Now, let us calculate the value of acceleration. One part we already found, normal reaction.